Ever feel like the universe is this incredible, ongoing story happening right over our heads, and we're only catching scattered chapters?
Definitely. It's vast and complex.
Well, today we're diving deep into that cosmic narrative. We want to give you a more, foundational understanding of some key astrophysics concepts.
And we're drawing from a great source for this, Neil deGrasse Tyson's Astrophysics for People in a Hurry. Perfect for getting the big picture.
Exactly. And what's immediately striking, as Tyson points out, is just the sheer audacity of the universe's tale.
Oh, absolutely.
Yeah.
I mean, we're talking nearly 14 billion years of history. And it all started from something smaller than a period on a page.
It's almost impossible to really wrap your head around. Less than a speck.
Right. And from that unbelievably tiny, hot beginning, it wasn't just a simple appearance. It was the Big Bang, this rapid expansion outward.
Okay, but trying to picture that very first instant, that absolute beginning, we hit some snags with our physics, don't we?
We really do. You've got our two heavyweight theories. Einstein's general relativity, describing gravity as curved spacetime.
Right, the big stuff, galaxies, stars.
Exactly. And then quantum mechanics, which handles the bizarre world of the very small atoms, particles.
The weird stuff.
The weird stuff, yeah. And they just don't play nicely together. Especially way back then in what we call the Planck era.
The Planck era. Okay, what's that?
It's this incredibly short slice of time, right at the start, from time 0 up to about 10 to the minus 43 seconds.
Wow.
Tiny.
Oh, okay.
And the universe itself was smaller than 10 to the minus 35 meters across. It's named after Max Planck, the guy who realized energy comes in little packets, or quanta.
So let me try to get this straight. In the Planck era, the universe was super tiny. Quantum rules should apply, but also unbelievably dense. So gravity, Einstein's gravity, was incredibly strong.
You got it. And our current physics.
Yeah.
It just can't handle both extremes at the same time in the same place. It's a huge puzzle.
A major frontier, you said.
Definitely. But the thinking is, right around the end of that Planck era, gravity kind of peeled off.
Yeah.
It became its own distinct force.
Okay.
Then, as the universe kept expanding and cooling really fast, the other forces started separating too.
Which ones?
First, what we call the electroweak and the strong nuclear force went their separate ways. And then a bit later, the electroweak force itself split into the electromagnetic force and the weak nuclear force.
So those are the big four we have today. Gravity, strong, electromagnetic, weak.
Those are the ones. They govern everything.
Yeah.
From radioactivity, that's the weak force, to holding atomic nuclei together with the strong force, atoms and molecules with electromagnetism, and, galaxies and planets with gravity.
So back in that super hot early phase, what was actually there? Was it just energy?
It was basically this incredibly energetic soup, lots of photons, light particles buzzing around, interacting with matter. But it was so hot that photons had enough energy to just spontaneously turn into pairs of particles.
Yeah.
Matter and antimatter.
Antimatter. Okay, that always sounds like sci-fi.
Huh. It does, but it's real. Predicted by physics, and we see it. So these pairs would pop into existence
And then
almost instantly annihilate each other, turning right back into photons. It was this constant back and forth, all governed by Einstein's famous E-motion, energy and mass, just converting.
So this soup, what particles were in it?
Well, this was the quark-lepton era. So you had fundamental particles called quarks and leptons. Electrons are a type of lepton, along with their antimatter versions. And also bosons, which are the particles that sort of carry the forces between the matter particles.
And quarks have those weird names, right?
They do. Up, down, strange charm, top, bottom. Just kind of whimsical.
Where did quark even come from?
Actually, a physicist named Murray Gell-Mann borrowed it from James Joyce's book, Finnegan's Wake. There's a line, 3 quarks for muster mark.
Huh, literature meets physics.
Yeah. And amazingly, scientists at places like Brookhaven National Labs, they've actually managed to create a state of matter called quark-gluon plasma. Sometimes they call it the quark cauldron.
A quark cauldron. Sounds intense. But wait, if matter and antimatter were always destroying each other, how did anything survive? How are we here?
That is one of the biggest mysteries. The best idea we have is that very early on, maybe when those forces were separating, something created a tiny imbalance.
Tiny how?
Like for every billion antimatter particles, there were 1,000,000,001 matter particles, just one extra.
1 in a billion? That doesn't sound like much.
It doesn't, but think about the scale. As the universe expanded and cooled below about 1 trillion degrees Kelvin, maybe millionth of a second in,
Okay.
the quarks started sticking together. They formed heavier particles called hadrons. Protons and neutrons are the most famous hadrons. And that tiny excess of matter quarks meant a tiny excess of matter hadrons.
So when all the annihilation happened between the matter and antimatter hadrons?
Exactly. For every billion pairs that wiped each other out, turning into photons, one single matter hadron was left over.
And that's what built everything. Stars, planets, us.
That's it. That tiny residue. Without that 1 in a billion asymmetry, everything would have just annihilated. The whole universe would be nothing but light. No matter at all.
Wow. That's mind-bending. Okay, so the universe keeps cooling, expanding. What's next?
Well, by about 1 second after the Big Bang, things had cooled more. The universe was maybe a few light years across. Still incredibly hot, about 1 billion degrees Kelvin.
Still hot enough for particles to pop into existence?
Hot enough for electrons and their antimatter partners, positrons, yeah. They were doing the same dance, appearing, annihilating.
And same story. A slight imbalance.
Seems so. Again, roughly 1 matter electron survived for every billion pairs that annihilated into photons. So now you have a universe with protons, neutrons, and a matching number of electrons, plus loads of photons and neutrinos.
Okay, so we have the basic ingredients for atoms, but it's still too hot for them to form properly.
Exactly. For the next 380,000 years or so, it was still too hot and dense. Photons just kept scattering off the free electrons like a thick fog.
Light couldn't travel freely.
Nope. But then the universe cooled below about 3,000 degrees Kelvin, roughly half the temperature of the sun's surface today.
And that was the magic number.
That was the point where electrons could finally slow down enough to be captured by the atomic nuclei, the protons and neutrons. They combined to form the first neutral atoms, mostly hydrogen and helium.
And that changed things.
Big time. Because suddenly, the photons weren't constantly bumping into free electrons. The universe became transparent.
Ah, the fog lifted.
The fog lifted, and the light that was bouncing around at that moment was finally free to travel across space. And that light, redshifted by billions of years of expansion, is what we now detect as
the cosmic microwave background radiation, the CMB.
precisely. It's like the universe's baby picture, a snapshot from when it was just 380,000 years old.
Incredible. So from that point, with atoms formed and light traveling freely, what happens? Gravity starts taking over.
Gravity really starts to sculpt things. Over the next billion years or so, slight density variations in that early gas cloud get amplified. Gravity pulls matter together, forming the first stars, and eventually vast structures we call galaxies, hundreds of billions of them.
Each with potentially hundreds of billions of stars.
Yeah. And inside those stars, particularly the really massive ones, something amazing happens.
Nuclear fusion, right. Making heavier elements.
Exactly. They start with hydrogen and helium, but under immense pressure and heat, they fuse them into heavier things. Carbon, oxygen, nitrogen, all the way up to iron for the biggest stars.
The stuff planets are made of, the stuff we're made of.
Absolutely. But how does it get out of the star? Well, those massive stars, when they run out of fuel,
They go supernova.
boom, they explode in these incredibly powerful supernova events. And that explosion scatters all those heavy elements they've created out into the galaxy.
Enriching the surrounding gas clouds.
Precisely. Seeding them with the raw materials for the next generation of stars and, crucially, planets.
Which brings us eventually closer to home, our solar system.
Right. So fast forward quite a bit, maybe 9 billion years after the Big Bang. In a fairly ordinary spiral arm, the Orion arm of a fairly ordinary galaxy, the Milky Way.
In the suburbs, basically.
Yeah, cosmic suburbs. A cloud of gas and dust, already enriched with those heavy elements from previous supernovas, began to collapse under its own gravity,
Forming the sun.
forming the sun at the center, and a surrounding disk of material that eventually clumped together to form the planets, asteroids, comets, the whole solar system.
And I gather the early solar system wasn't exactly peaceful.
Not at all. It was a cosmic shooting gallery for a long time. Lots of leftover debris smashing into the newly formed planets, a period of heavy bombardment.
Leaving scars and probably making it hard for complex chemistry for life to get started initially.
Definitely delayed things on the rocky planets, yeah.
Yeah.
But eventually, things settled down. And we ended up on a planet, Earth, particularly rich in certain elements.
It's like carbon. You mentioned carbon is key.
Carbon is incredibly important. Its chemistry is just uniquely versatile. It can form long chains, complex structures. It's the backbone of all life that we know. Its abundance, cosmically speaking, is a big deal for life's potential.
It's amazing tracing it all back. But life, once it got going, wasn't always secure, was it? Use the dinosaur example.
Right. The asteroid impact, 65 million years ago, down near the Yucatan Peninsula. A huge rock, maybe 6 miles across.
Trillions of tons, Tyson says.
Yeah, caused a mass extinction, wiped out maybe 70% of species on Earth, including, famously, the dinosaurs who'd been dominant for ages.
A catastrophe.
A total catastrophe. But it cleared the stage in a way. It opened up ecological niches. And our little mammal ancestors who'd been scurrying around in the shadows,
They got their chance.
they got their chance. They diversified, evolved, eventually leading to primates and, well, eventually to us, humans, capable of looking back and figuring all this out.
It's a wild chain of events. It's just improbable. But what about the very beginning, before the Big Bang? Does physics have anything to say?
That's where things get really speculative. Our current physics, general relativity and quantum mechanics, they break down at time zero, at that initial singularity. We just don't have the tools yet.
So ideas like a multiverse or the universe just popping into existence.
They're out there. Interesting ideas. The multiverse, maybe countless universes constantly forming. Or maybe our universe quantum tunneled into existence from, well, nothing. But these are more philosophical or at least highly theoretical at this point. Not much hard evidence.
So it's okay to say we don't know.
It's absolutely essential in science. Admitting ignorance is what drives us forward. It points to where the next discoveries might be.
Okay.
What we do know, or are very confident about, is that our universe had a beginning in this hot, dense state. We know it's been expanding and evolving ever since. And we know fundamentally where our atoms came from.
Right. From the Big Bang itself, the hydrogen and helium.
And from the cores of stars that lived and died long ago, forging the heavier elements inside them and then scattering them.
Which leads to that amazing line, we are stardust brought to life.
Then empowered by the universe to figure itself out. It's kind of poetic, but it's also literally true.
It really is humbling and, awe-inspiring to think about that entire journey.
From that fraction of a second, that tiny hot point, to galaxies, stars, planets, and us sitting here talking about it. It's an incredible story.
It really is. We've covered so much ground in this deep dive, from the first moments to the formation of everything around us. And the takeaway, I think, is that connection.
Yeah, despite the mind-boggling scale, the vastness of space and time, we are fundamentally part of it all, connected at the atomic level.
Makes you really pause and consider our place in it all, doesn't it? This tiny corner of the cosmos, yet somehow able to comprehend at least some of its grandeur.
It's perhaps the most remarkable thing of all.